Hello, can you
Hey
hear me?
Madison, good. Hello,
Oh,
hello. How are
am
you?
I volume down? Hello?
Hello, hello. Can you hear
Oh,
me?
yeah, I can hear you.
I see, I see. That's good. Today we're gonna do like the post lab questions that you sent me. And then after that, if you have your graded quiz one, we could go over that and like go over the mistakes so that you can learn from the mistakes. And then
Oh
after
no.
that, we could go over like the midterm, like the no, not midterm, the new material.
I don't
Yeah.
think you want to see my quiz one. It was so bad.
That's okay. It's okay. You could just send me like what question do you want to go over? Like you don't have to actually send me the quiz uh like graded quiz PDF. You could
Oh,
actually just send me like the problems and like what they are, so then we could like go over them. Like
okay.
on message. Yeah. You don't
I
have
mean,
to
I
actually
don't really
send your
care either
grade.
way.
Uh-huh.
You're here to help me, like,
Yeah.
you know what I
Yeah.
mean? But
Yeah.
it was
Yeah.
rough, but it's okay.
I see, I see. Like, did you feel like the time was the issue, or was it like the old
No,
material?
I don't know. Like, I feel like I just, like, I wouldn't have done as well as, like, I didn't do great at all. Like, I got a, like, 30,
Uh-huh.
six or something to 66, but I
Uh-huh.
I don't even think I would have gotten that if I didn't like go to your stuff. So like
Uh-huh.
I think it's just like all like learning, relearning everything. I feel like
Relearning everything, yeah, because like
yeah.
the last time you took OChem was like a long time
Over-
ago.
Yeah, over a
Yeah,
year ago.
right. Let's see. Um, so let's see here. We'll get started with the post lab questions.
Okay.
The first question is asking you to write out the mechanism for the reaction of 2-methyl-2-butanol with concentrated hydrochloric acid. Are you familiar with how to convert this IUPAC nomenclature into like let's say bond line structure?
Like I know that 2-methyl, like there's a methyl group on carbon 2,
Mm-hmm.
and then is there also a butanol group, a butanol
A butanol,
on
where
as well?
when you see OL here, what functional group would be the main functional group, the main priority functional group in the molecule here?
An alcohol?
An alcohol, yes. And based on the main chain, what's our longest carbon chain? Like based on butanol, what does that say about our longest carbon chain? How many carbons are in the longest chain?
I know it. I know the beginning. It like tells you what it
Uh-huh.
is. I need to memorize that. I think it's
Uh-huh.
like, is it five?
Five would be pent. So let me write it down.
I
One,
put
think of it as mono. Oh wait, for there's different things actually, depending on what it is. So, uh, prop, meth. So one, if it's one carbon, then that would be just like meth, like methane.
uh-huh.
Uh, two would be like ethane. Three would be propane.
Oh, it's four is but.
Yep, four is but.
I see.
Five would be pent. Six would be hex. Seven would be hept. Eight would be oct. Nine would be known, non. 10 would be deck, like that, right? So, because we have butanol, that means our longest carbon chain here is 4 carbons long, and I'm gonna draw that out like that. That's our longest chain right there. One, two, three, four. So I'm gonna now number it like this: one, two, three, four. We see that at carbon 2, there's a methyl group and an alcohol group. So I'm gonna draw it like this. At carbon 2, I'm gonna draw the methyl group coming out like that, and an alcohol group coming out like that.
Okay,
Mhm. Okay.
got it.
Yep. So now um we're gonna react this with concentrated hydrochloric acid, which is HCl. So concentrated, think of it as an excess amount. HCl, excess amount. So this is an alcohol reacting with a nucleophilic acid HX, right? Where
Hmm.
X is like a bromine, chlorine, iodine, something like that. So let's think about the mechanism here. What do you think is gonna happen between that strong acid and this alcohol here? What's gonna be the first step of the mechanism?
Doesn't it doesn't break off. The OH attacks
Yep.
or like wants to
Mhm.
bond with the hydrogen and HCl.
Yep. Mm-hmm. oxygen attacks that hydrogen from HCl, kicking out the Cl, and
Mm-hmm.
that would convert this poor leaving group, the alcohol, into a good leaving group, water. So that OH would become OH2, and because this oxygen here has 3 bonds, 1, 2, 3, it would have a positive charge. And when you see this OH2 plus or H2O plus, that is now a good leaving group, right? And because we have a tertiary alcohol, right? This is a tertiary
Mm-hmm.
alcohol. If we look back at the table we made with the HX and alcohol reaction, this is gonna be an SN1 reaction, right? So I think you needed help with that too, like determining what kind of reaction
Yes.
would it be, like SN2, SN1, or E1. So the way that I like to think about it is that SN2 reaction, SN2 like reactions tend to work
Mm-hmm.
with primary substrates, right? Because we want the nucleophile to attack the less sub carbon. There's no carbocation intermediate. So let's say that no carbocation intermediate. And for second for SN2, let's say it's primary unhindered, right? Where the carbon next to it is not branched.
Right.
For SN1 like reactions, you could see primary hindered,
Mm-hmm.
secondary, or tertiary substrates. And these reactions will have multiple steps where you will have a carbocation intermediate.
Right.
And this carbocation intermediate here is going to be more stable when there's more alkyl substituents around it.
Mm-hmm.
Right? Like if you just have this methyl carbocation versus this primary carbocation versus this secondary carbocation versus this tertiary carbocation, the more alkyl groups that are around the carbocation, the more stable it's going to be, right? And that's because of a factor called hyperconjugation, right? I think of it as like the more friends it has, the more stable it's going to be.
Right.
Less energy, right? Okay. So that's why SN1 prefers to react with more substituted substrates. If we have a good leaving group here, and let's say that we just kick off the leaving group by itself, it just leaves by itself. When we do that, we're going to form a tertiary carbocation, right? Because this carbon right here that I gave the positive charge to lost a bond. Before it had 4 bonds, 1, 2,
Mm-hmm.
3, 4, but when we kick that leaving group off, it lost the bond. So that's why it's gonna have a positive charge there now. So SN1 is gonna be the reaction here because we can form a stable carbocation. Whenever you see like a methyl carbocation or a primary carbocation, they are too unstable to exist. Too unstable. Right, so let's say instead of having that alcohol, let's say we have a primary alcohol, primary unhindered alcohol reacting with HCl.
Right.
The first step is always going to be the same. Protonate the alcohol oxygen. That oxygen alcohol is always going to attack the H, kick out the Cl minus, convert that bad leaving group into a good leaving group.
OH plus. Okay.
Yeah,
It gains
OH.
it gains a hydrogen bond, right?
Yes, it
So
gains
then
it. Uh-huh.
it technically has 1, 2, 3, 4.
It has 1, 2, 3 bonds and 1 pair of electrons.
Okay.
Right.
Got it.
Before it only had 2 bonds, 1, 2, and
Oh.
2 pairs of electrons. But we're using one of its pairs of electrons to grab this H right here to make a bond with that H.
Okay.
Right. So if I want to draw this out more like in detail, this oxygen here has 2 bonds originally, a 1 bond to carbon, 1 bond to hydrogen. But now it will have 3 bonds. 1 bond to carbon, 2 bonds to hydrogen, and 1 pair of electrons now.
Oh, I see. Okay.
Yep. Uh-huh. because it used one of its pairs of electrons to make this new bond right here. This new bond right here came from that pair of electrons right there, right? And this bond right here between H and Cl, those two electrons are gonna kick off onto chlorine, making Cl minus like that. Right?
Okay, got it.
And when we calculate formal charge is how many electrons the atom wants based on the group or column in the periodic table minus how many they actually have. So if we calculate the formal charge of this oxygen right now, Fc, oxygen is on the 6th column of the periodic table, 6th group. So it wants 6 electrons to itself. But right now we see that it has 1, 2, 3, 4, 5 electrons to itself.
Right.
6 minus 5 is positive 1. That's why it has a positive 1 charge. When you see oxygen with 3 bonds and 1 pair of electrons, it's a positive charge. If we do the same for this oxygen right here, this oxygen has 1, 2, 3, 4, 5, 6 electrons to itself. 6 minus 6 is 0, neutral. Right. But this
if it was like, if say it had like 6 minus 7, so then it would be a negative charge.
Yes.
Okay.
It would be a negative charge.
To clarify.
For example, something like that would be this oxygen here with only 1 bond and 3 pairs of electrons.
Okay.
Right. 6 minus 7, negative 1 charge, like that. Right.
Okay.
That's good. And this right here, the water part, H2O plus or OH2 plus, is going to be our good leaving group. Let's say that the leaving group leaves, right? Just imagine when it leaves, we form this carbocation. Is this a stable carbocation?
No.
No, right. It is a primary. Oh, wait, actually, let me just write this down so then, like, we know not to do that, right? And make an X right there. If that leaving group leaves, we form water, and this primary, unhindered carbocation. It's unhindered because if you look at the carbon with the positive charge, the carbon nearby only has 1 branch. So it's unhindered, unbranched. So that is too unstable to exist. So this route would not be formed. We won't do SN1 here. We're going to do SN2, right? So the Cl minus that we kicked out earlier that we formed is our nucleophile. That's going to attack this partial positive carbon, right? And then kick out the leaving group, SN2 reaction. So that's only like one step. Once we have the good leaving group, we do the backside attack and substitute the leaving group with the nucleophile in one step. No carbocation intermediate gets formed because we cannot form a stable carbocation intermediate.
Okay.
Right. Now, let me show you the rare case that she was talking about. Right, that's the one with primary hindered substrates. So you could either do a concerted hydride shift or methyl shift. On her lecture notes, she did a concerted methyl shift. So that's a little bit trickier than hydride shift because it's gonna look a little bit more funky, a little bit more weird with the moving methyl group. Methyl shift. So let's just look at an example with concerted hydride shift first, and then we'll do concerted methyl shift after. Right. So let's say we have HBr here. First step, protonate the alcohol, grab that H, kick out the Br minus, convert that OH into OH2 plus, good leaving group. And if we kick that out directly, we form this primary hindered carbocation. This is still a primary carbocation, so we cannot do that. Wait, so let me draw this purple arrow, kicking that out, an X right there, X right here, to show that this is still too unstable to be formed. Too unstable, because it's still a primary carbocation. We do not want to form primary carbocations at all. Right. But what we can do is that, you notice how the carbon here holding the leaving group, the nearby atom is branched. It has more than 1
Right.
constituent.
Yeah.
If it is branched, then we could do a concerted hydrogen shift or methyl shift. If it has a hydrogen, then we prefer to do a concerted hydrogen shift, right? Because we
Okay.
do have two methyls here, two methyls, and we have
Mhm.
one hydrogen. We prefer to do a hydrogen shift because it's smaller and it requires less energy to move like that small atom than
Right.
the methyl bulkier group. Yeah, right. So this hydrogen here with the bond, I'm gonna highlight it in yellow. Like that hydrogen with the bond is going to shift over to that carbon and kick out the leaving group at the same time,
Right.
simultaneously, right? And that's gonna form us this intermediate. And you don't actually have to draw out this bond with the hydrogen. You can leave it as invisible. But if I want to track it, like where this hydrogen went, it's this hydrogen over here, right? And you notice how this carbon here, it used to have 4 bonds, 1, 2, 3, 4. It now has 3 bonds. So what would be the formal charge of this carbon here with 3 bonds and 0 pairs of electrons?
One, one, two, three, four. Wait, one, two, three,
It has 3 electrons to itself. And how many electrons does carbon want to itself? What group is it on in the periodic table?
6.
That
Right.
would be oxygen.
Oxygen has 6.
Yep, oxygen has 6. Carbon is 4.
So it has a positive
Yep.
charge? Okay.
Yep, because 4 minus 3,
Yeah.
positive 1. Carbon would be 4, nitrogen would be 5, and then oxygen would be 6. Right.
4, 5, and 6. Okay.
And then all the halogens, the X's, like chlorine, bromine, iodine, are 7s.
Are 7s.
Yeah.
Okay.
4, 5, 6, 7. Those are the common ones. 4 for carbon, 5 for nitrogen, 6 for oxygen, and then 7s for the halogens.
Okay.
Right. So this carbon here with 3 bonds will have a positive charge right there, right?
Okay.
Making that our carbocation. Okay. Now, once we have that most stable carbocation, then like whenever we form any sort of carbocation in any sort of reaction, we always have to look out for any hydride or methyl shift. But it's already in its most stable position, so we don't have to do any hydride or methyl shifts after this, right? Because it's already in its most stable position here. Once we have that most stable carbocation, the Br minus or X minus will come back and attack that carbocation, making a new bond between that carbon and the halogen, right? This is the new bond right here.
Okay. 1, 2, 3. Okay.
Right. Because you could think of it as that this halogen here has 4 pairs of electrons.
Right.
So it has 8 electrons to itself. 1, 2, 3, 4, 5, 6, 7, 8. 7 minus 8, negative 1 charge. It's gonna use one of its pairs of electrons to make that new bond right there. Right. The 2 electrons in that bond are coming from the 2 electrons from one of its pairs of electrons. Right. And now this halogen here has 1 bond and 3 pairs of electrons, making it neutral. Because it has 1, 2, 3, 4, 5, 6, 7 electrons to itself. 7 minus 7, 0. Neutral. Right. Okay, so that is the rare case. Now let's look at an example of a concerted methyl shift. If I have something like this, and I react it with HCl, first step is the same. We have a bad leaving group here. We can't do anything with this bad leaving group yet. But if we have a strong acid, we can convert that bad leaving group into a good leaving group by protonating it like that. Right. Okay. Now, can we form a stable carbocation directly here? Like, can we just kick off the leaving group and do nothing else? Like, what happens when we just kick off the leaving group?
If we just kick off the leaving group, then doesn't it become like unstable?
Yeah, because this carbon here is
Isn't
gonna be the
that just a
carbocation.
carbocation?
And what kind of carbocation is this? Like, primary, secondary, tertiary?
Tertiary? Or wait.
How many other carbons is this carbon here attached to? One other carbon right here. Right. So that would be
I think like I'm trying to connect all 3 of the branches, but it's just like the most immediate one.
It's the most
Correct.
immediate one. Correct. Don't think about these ones. These ones here are
Yeah.
too far away.
Okay.
Yeah. So because this is a primary carbocation, this is too unstable to exist. We cannot do this right here. Right. But you notice how this primary carbon here is hindered because right next to it is branched. It has like more than one substituent, I'm gonna highlight one of the methyl groups here and shift that methyl group over to this carbon and kick out the leaving group at the same time.
Okay.
When that happens, I'm going to have this intermediate where the methyl group that I highlighted is now here. And we actually have to draw that out now because it's not a hydrogen. We can't make it invisible. We actually have to
Right.
draw out that hydrogen right there. I mean, methyl right there. Right. And then once we have this carbocation, the most stable position, then we bring in the Cl minus back to attack and form our final product. Like that.
And it attacks at that it attacks the carbocation or essentially the carbon, right?
Yes,
Okay.
the carbon, because this carbon here with the positive charge is the carbocation. It is missing 2 electrons, right? And because it's missing 2 electrons, it has like a void. It wants to accept the electrons, and it's going to accept the electrons from the chlorine's pair of electrons here, right? To
Right.
make that new bond right there. That
Okay.
new bond fulfills this carbon's void, making it neutral and stable.
Okay, got it.
Yep. So that are the rare cases. And if you have a primary one with an unhindered substrate right here, we
Mhm.
could not do that at all, right? Like we couldn't do the considered hydrogen shift like that for this one.
Right.
If this was primary unhindered, then we would go through SN2 reaction, right? No carbocation intermediate at all. Cl minus attack the substrate and kick out the leaving group right away.
But the hindered is a SN1 reaction, correct?
Yes, the primary hindered is an SN1 reaction. Yes.
Okay.
Unless you have high temperature, like 180 degrees Celsius, then you would do E1. Right.
Okay.
But that's more for H2SO4. When you say HX, I don't think you get that. That's more for H2SO4. Right.
Okay.
We'll go over that chart later, but this is the HX one.
Okay, perfect.
Yeah. So now once we have this right here, this good leaving group, we're just gonna kick it out by itself because it can form this stable tertiary carbocation that could exist by itself.
Right.
Right. Now after that, what do you think is gonna happen next here? After we form that carbocation, the most stable carbocation intermediate.
It's gonna the Cl attacks the carbon where that intermediate's at. And then it's gonna form a new branch there where
new bond.
Or yeah, a new bond where that carbocation was. So
To a chlorine atom, right? This is the new bond right here.
attacks and attaches, correct?
Yep, it attaches onto that carbon right there. Yep.
And then that's your final product.
Yeah, that's your final product where this is our SN1 product right here.
Right. Okay.
Whenever you have SN1 product or reaction, they always are accompanied with an E1
Okay. Cool. I got
reaction.
that.
Yep. And SN1 would always be major in room temp when heat is added, or when you're in hot temperature, then E1 would be major, right? But we're not in the heat here.
Oh, I see. Okay. Is it the same flip side for SN2 and E2? Like whenever heat's added at like a lower temperature, you do 2?
Yeah, it's the same for SN2 and SN1. SN1 and E1, they always go together, but SN2 does not always go with E2. For alcohols and H2SO4, then it's always like that, like SN2 and E2. If you have a primary alcohol, wait, let me check the chart here really quick, just to make sure before I give you that information. Right. Let's see here. Let me see what Liebman says about this one. Let's see. Primary alcohol, SHI. Let's get H2SO4. H2SO4 and heat. E2, yeah.
Is it on any of those resources or anything?
Yeah, I found it. She did do SN2 and E2 for a primary unhindered substrate, but she did like I'm trying to find like when you use which one because primary alcohol they don't make carbocation intermediate, so they go through E2 with H2SO4, but the primary unhindered one you could get elimination because present molecules can always react with itself. Mostly primary, but can also be with side reaction that forms ethers. Primary alcohol. Don't make. Yeah. So this one here, it would be the same. If you have temperature, then that would also affect if you have SN2 or E2. If you have high temperature, then you want to favor E2 elimination reaction. If you have lower temperature, you favor the substitution reaction, the SN2 reaction.
Okay.
Right.
Okay.
Yeah. So the mechanism would be that where the major product is going to have a chlorine substituting the OH like that.
Okay, perfect.
The mechanism of this is SN1 is accompanied by an E1 mechanism, which will give the alkene side product.
Right. And SN2 and then E2 also run together as well, correct?
They usually don't run together. They're usually separate.
Oh, are they separate as well?
The reason why is because well, for normal SN2E2, they're separate, but with alcohol and acids, that they could run together.
Okay.
Right? And it's based on the temperature. If it's in low temp, then SN2 would be major. If it's in high temp, E2 would be major. Right? So in alcohol reactions, like in these reactions we're doing within acid, they can run together.
Okay.
And temperature would be the one that determines what's the major one, major product. Right?
Okay.
Okay. So the question here is asking us to write out the mechanism of the formation of the alkene side product. So this is our 2-methyl 2-butanol reacting in HCl acid. The first step is always the same. Protonate the oxygen, kick out the chlorine, convert that bad leaving group into a good leaving group, OH2+. We can form a stable carbocation right away by just kicking off the leaving group to form that carbocation right here. Once we have this
just asking for the same thing over again, essentially?
No, not the same thing over again, because the last mechanism we did SN1 mechanism.
Okay.
This one here is asking us to do the E1 mechanism, because the E mechanisms like E1, E2, they always form alkenes.
I see. Okay.
Extra bond, right? But the first few steps of SN1 and E1 are always the same.
Okay.
Yeah. They always get to the most stable carbocation intermediate, right? After like some shifts, if possible. In this case, we don't have to do any shifts because it's already in its most stable position. Once it's at its most stable carbocation position, then this is when we choose to do SN1 or E1. This is when it gets different, right? For SN1, the nucleophile just attacks the carbocation.
Right.
For SN1. For E1,
doesn't it attack the branch or something?
It attacks one of the branched hydrogens. This is the substrate carbon. These are the alpha carbons. The first carbon attached to the substrate carbon, the immediate carbons. Like the carbons directly attached to the substrate carbon right here. Those are the alpha carbons. I'm gonna draw out at least one alpha hydrogen for each alpha carbon. Like that. Now, let's say this is hydrogen A, hydrogen B, hydrogen C. Which hydrogen do you want to grab to make the more stable double bond?
More stable. Is it hydrogen C?
Hydrogen C, because it's the most substituted one, right?
Because it's got two, like essentially it's attached to one carbon, but it's got two on the side.
Yeah.
The other ones just have one.
Yeah. Right. that one carbon here is attached to two carbons. The other carbons here are attached to only one carbon, right? So you can think of this as primary, secondary. Yeah.
Right. Got it.
So the base that's going to grab that, in this case here, is going to be the Cl minus that we have floating around, right? That Cl minus base is going to grab that most substituted hydrogen to form HCl, right? This is going to form HCl as a side product. So if we draw the arrow, HCl will get formed as a side product. But when this chlorine here is grabbing that hydrogen, this bond right here between the hydrogen and carbon, right here, those two electrons are going to make a double bond right there. An alkene like right there, giving us this alkene right there.
Oh, okay, I see. So it attacks the hydrogen, and then the hydrogen breaks off, and then it attacks that bond. Or
yes.
It attaches onto it.
It attaches onto it. Right. It just like shifts over to make a double bond right there. And that's able to happen because you notice how this carbon here is missing 2 electrons. It only has 3 bonds. It wants this bond to go over there to make a double bond, because now when that happens, this carbon now has 4 bonds and it's now neutral. No more carbocation.
Okay, yeah, that makes sense.
Because this carbon here has 4 bonds now. 1, 2, 3, 4. But this carbon here lost the HC, right? That carbon HC is lost because this chlorine here grabbed that HC to form this HCl here. Right. Now for Leeuwen's midterms or quizzes, this is not the only alkene product we have here. This would be the major one because it's the most substituted one, right? But oh, actually, no. In this case, it would be the only one because if we did rotation here, if we rotate that single bond, we would get this here anyway. But let me give you an example of one that would give you different products.
That makes sense. No, I remember her going over. I think vividly, not vividly, but briefly going over that. Because if you rotate it, sometimes the bonds like change and stuff.
Yeah, it does. It does. Right. Because let's say we have this and our base here, instead of Cl minus, we're gonna use HSO4 minus coming from H2SO4. Right. What would be your next step here? Like, what's your thought process here? Once we have this carbocation and we want to do E1, let's say we have high temperature, 180 degrees. What would you do to predict the alkene here?
So we first look at the like its position to make sure it's in, because it's a carbocation, to make sure it's in the most stable position. It's in the most stable position. So then the hydrogen, you would look, alpha and gamma, you would look at the most substituted hydrogen.
Most substituted alpha hydrogen. So
alpha hydrogen. So the 3 that are closest, are correct?
Correct.
In this case.
Actually, there's 2 hydrogens that are the same here. The same substitution. So let me change this up and add that right there. This is alpha.
Okay. The most substituted one would be the one on the far right.
It would be on the far right. Let me add a methyl group right here too, just to show you the different reactions.
Right.
The different alkenes.
So then that charge would attack the hydrogen, and then that would then attack the bond between that center carbon, or the carbocation is in the hydrogen.
So this bond here between the hydrogen being grabbed and that carbon breaks and goes to make a double bond right there.
Yeah.
Between the substrate carbon, right, the carbocation carbon.
Yeah.
And this alpha carbon right there. like that.
Yeah, is that right?
Yep, that's right.
Okay.
That's right. And based on those two arrows that we just drew out, we're gonna make these products here. That alkene and H2SO4. Right. H2SO4 comes from this HSO4 minus grabbing that H to make H2SO4.
Oh, okay.
Because
And
in our
essentially, and the hydrogen bond is just attaching to that bond. It has nothing to do with the HSO4 because that's separate. It's still floating around.
this H right here.
Yeah, because it's grabbing the hydrogen.
Yeah, this HSO4 minus here is grabbing that hydrogen, which is why it's now H2SO4. Before it only had one hydrogen, but now it has two hydrogens because the second hydrogen is that hydrogen it grabbed right there.
Right, and then that bond is like kind of free floating around, so then it wants to attach to something.
Yeah, that bond is free floating around. It has to go somewhere, and it's gonna go to make a double bond right there.
Okay.
Right, which gets rid of that positive charge, gets rid of that positive charge to make it neutral right here.
Right. Okay. Got it.
Now this is one of our products, right? But I'm gonna show you another type of product that we can get here. So let's say we have the same carbocation, and we rotate that single bond right there, swapping that methyl group with that ethyl group right there. So we're gonna switch those two groups around and have this rotated structure here. Ethyl group down there, methyl group right there, positive charge right there. And let's say we grab the most substituted alpha hydrogen still with HSO4 minus. Grab that, make a double bond there. We would get this alkene here with H2SO4 as well.
So it's just essentially like flip?
Yeah, we just flipped one side of the alkene substituents.
One side, yeah.
One side. This side here stayed the same. Like the left side stayed the same.
Like it's rotated on that carbon.
Right, rotated on this carbon right here.
Yes.
Yeah. Between the substrate carbon and that most substituted alpha carbon right there.
Let's see. Okay. That makes sense.
Yeah. Which one would you say is major and which one would you say is minor?
Oh boy.
And to help you, which one is E and which one is Z alkene?
I think that because a double bond is it the first one E?
Yeah, first one is an E alkene. Second one is a Z alkene.
Oh, because whenever you like slice it, the E is like opposite sides and then the Z is same side.
Yeah, that's right. We see the two highest priority groups here are on the opposite side for E, and the two highest priority groups here on the bottom are on the same side.
Okay, and the major product is an E?
Yeah, major product is an E.
And then Z is non-major?
Yep, minor, non-major. And what's the factor that helped you distinguish that?
Isn't that the like stereo?
Steric hindrance.
Steric hindrance.
Okay. Because steric hindrance is how like parts of a molecule bump into each other.
Right.
And we don't want that, right? Because this bulky group here and this bulky group here, they're so close to each other, they're gonna bump into each other. That's not stable. That's called steric hindrance. More steric hindrance makes it less stable, minor. Right.
But the first one, they won't bump into.
Yeah. They're on opposite sides, so they won't bump into each other. They're as far away from each other as possible.
Right. Okay. Perfect.
Now you can even have more minor products than this, right? Because if you grab this alpha hydrogen with HSO4 minus and make a double bond there, you're gonna form this sort of alkene right here, which is not as substituted as these two alkenes right here.
Okay, that makes sense.
Right. But I don't think you have to put that in the product, but that is a like possible minor product. Like that's minor product.
Right, something to note.
Yeah.
Okay.
Something to note for like vocab or something just in case it shows up on the mechanism or vocab.
Okay.
Yeah. Okay, so let's go back here. This is the mechanism for the alkene side product here, E1. Why do we not see any alkene side product in our chain? So there are a couple of reasons. SN1 is major over E1 in room temp or low temp, right? Once we get to high temp, then E1 would be major, right? Also, another reason is that because we have concentrated HCl or HCl in excess, any alkene product that we do form, any alkene will react with the concentrated HCl.
And so that's why there isn't like side product, because if there was an alkene, it would like react and essentially like not be there.
That's correct. And that's what the next question is asking about, right? Because let's say that we do form this alkene here in minor product. That alkene right there is still in the presence with HCl. There's still HCl floating around.
Yeah.
What would happen between this alkene and this HCl here?
Wouldn't the bond break off?
The bond, so alkene reactions, we want to form the more stable carbocation intermediate with HX. We could either form a carbocation here or here. Okay. We want to form the carbocation here on the left side because it's more substituted, more stable. We want the positive charge there. If we want the positive charge there, then that means that the less subcarbon right here is going to grab the H and kick out the Cl, right? Break off the carbon alkene and grab that H, kick out the Cl right there. Right.
The Cl would come back and then attack that carbo.
Yes, but in this case, like we always have to look out for any shifts, rearrangement before we do that. But in this case, we didn't have to do any of that because it's already in its most stable position.
Right.
Right. And then the Cl minus will come back and attack the most stable carbocation to give you that product right here, where that's the same major product as the SN1 product that we did right here.
Oh, I see. Okay.
Right here. Yeah. Right.
Yeah.
SN1. And that's why when you form any sort of alkene, it would convert into the major product anyway.
Like it just reverts back. It like kind of just like.
Yeah. You can think of it as like it reverts back into this major product. Like all would go to this products here. Like all alkenes would go to this major products because we have excess amount of HCl there.
Right.
Because it doesn't technically revert back because it didn't come from this. This alkene here came from this alcohol here. Right. So it did not like revert, like go backward here. It just kept going forward to go to the major product here. Like the SN1 product, you could say. But this right here didn't come from SN1 reaction.
Yeah, right? That's like SN2?
Not SN2. When you see an alkene reacting with HX, this reaction name, or there's a couple of reaction names for this. You could think of it as, like, in simple terms, addition of HX or hydrohalogenation. But the mechanism is electrophilic addition. Electrophilic addition. So it's not SN2, SN1, because SN2, SN1, E1, E2, all those reactions, they need a good leaving group. Like SN2, SN1, E1, E2, they need a good leaving group. This alkene here has no good leaving group at all. The reaction of this is addition of HX or hydrohalogenation, but the mechanism is electrophilic addition because we're think of this hydrogen here, the positive charge hydrogen here is the electrophile. We're adding the electrophile onto the alkene, right? So that's why it's electrophilic addition. And then the Cl minus would just come and attack the carbocation. Like that's the name of that mechanism right there.
Electrophilic addition.
Yeah.
I've heard of that.
Yeah, that's for alkene reactions. A lot of alkene reactions. I think that was 8A. I think it was 8A.
Oh, really? I missed
Yeah. A lot of alkene reactions. 118B is learning about this right now.
Oh, really?
Yeah, 118B is learning about these electrophilic alkene reactions. Yeah. So
steps.
yeah, there are like a lot of like carbocations involved. And this Monday I have the review session, so like you can like come by and like review because like all of it is gonna be alkenes and electrophilic addition reactions. Yeah, but that's gonna be like more review for you, like for you, because that's more 8A. Yeah.
Yeah, just to kind of go over. That'd be really good, actually.
Yeah.
Listen.
Yeah, it's good. Yeah.
Perfect.
Yeah.
Some of these post labs, like at least like that stuff, also gets me. I understand like the math part of it all.
Oh, like the Roots law, like all this stuff right here.
Oh yeah, like the Gen Chem stuff.
Like I have no idea how to do this right here. Like I have no idea. Yes, like I forgot what Roots law is. I haven't seen moles in so long. Vapor pressure, molar mass, boiling point. Oh, boiling point kind of makes sense.
Math, that's fine. It's just like the breaking down of everything is like all fair to me. But I guess it's a lot of patterns and stuff, right?
Yeah, like for like the post lab questions here.
And like recognition, like as far as like doing these mechanisms and stuff.
Yeah, and a lot of understanding as well, like conceptual questions, like energy, stability. Like cause sometimes it could be tricky questions that are different from one another, and then like there's a smaller difference, like a hydrate shift versus a methyl shift. Not every reaction is the same. Like you have to like know the specific details and understand like very like deeply about the mechanism, each step, one by one. You know, each arrow.
Have you been doing this for?
Like tutoring or when did I take OChem?
Both, I guess.
Oh yeah.
Like, how are you tutoring and like how did you start and stuff?
Yeah. So I started UC Davis 2020. That was like the lockdown COVID year.
Oh no.
No. So all my first year was online. Like I did not have a Davis dorm experience at all.
Right.
And then my first year after like that, like the summer after my first year, it was still online. I decided to take OChem. I started like 118A and B over summer session 1 and 2, but it was online. So like it was a little bit easier because like on the test you get to use like notes even though you're not supposed to, but then I had it next to me.
Yeah.
Yeah. But it was so fast though. It was like 6 weeks for like 1 quarter.
Yeah, that's insane.
But that was all I focused on, like OChem that summer.
Yeah, that kind of helps a little bit, but you just understand it so well, obviously.
Yeah, but I had to like thank a tutor because the Discord server had a like really great tutor, and then like he tutored me, and a lot of like current tutors right now, from AETC and the big Discord server.
Oh wow.
Yeah, but he's no longer active because he's in grad school for OChem. Like he's active in labs at OChem.
Oh really? Oh
yeah.
Are you in grad school then too for chemistry or anything like that?
Not in chemistry. I'm in grad school at chiropractic school.
Oh my gosh, seriously. Oh my gosh, that's so cool. So that's why I had to take OChem. What did you get your degree in?
Biochemistry.
Oh my god.
Yeah. Are you pre-vet?
I'm animal science and management. So like essentially, yeah. I also take like econ classes and like management classes as well as like the sciences.
Yeah. Do you ride horses at Davis?
I do, not at Davis, but I did at home. I like transferred here, so I rode like that was like my career for a bit. And then I was like, oh, I got an offer, like because I just did my CC and I was like fine with my associates. But then I like just applied to schools just in case, and I got financial aid to come up here, and I was like, well, I'll just
Yeah.
knock it out while I can and
Uh-huh.
get it done. But yeah, I
Yeah.
ride horses. Just I not like here for like the team or anything.
Oh yeah, because there's the racing one, but like there's the one for like just for fun, right? Like the the horse riding classes or something like
Yes, yes,
that.
they do that. I haven't seen those, but those look really cool. Um,
Uh-huh.
you know Jenna too, and me and her work
Yeah.
together actually at the same place. So
Oh, what do you guys work as? Like just like cleaning the taking care of the horses or like
yeah,
training
it's
them?
the Center for Equine Health. It's affiliated with Davis. It's like an extension essentially of like the vet program, like the vet hospital.
Hmm.
So we have like horses that are like rehabbing and stuff from surgeries or
Oh, yeah,
they've got going
yeah.
on that don't
Uh-huh.
quite need to be at the hospital, but still need like surveillance like 24 hours. So we do
Hmm.
like a lot of like med administration, and then they also house the horses there that the vet students practice on, like
Hmm.
different procedures and stuff. So it's like a bunch of like older horses that they just kind of like use.
Yeah.
They have different problems, so they do
Mhm.
studies and all that on all those ones.
Yeah, it's interesting.
Yeah, it's fun. It's a good little like brain break too, like from school to like go out there and like work for a bit and then
Mhm.
come back.
Yeah. I see. That's good. Um,
Are you in school in Davis then still
no,
or?
I'm back at my hometown, San Jose.
Oh my
Because
gosh.
my chiropractor is in Hayward, so it's a 30-minute commute there.
Oh
45-minute
wow.
commute back, yeah.
Holy moly.
But I will visit Davis like at the end of the quarter for final review sessions in person.
Oh really? Oh
Yeah.
fun. Okay, that's so cool. That would be awesome. I'm
Uh-huh.
surprised nobody's in here right now.
Oh yeah, like no one that shows up to this Friday one. Like I never had this Friday one. I just added it this quarter. So like you're the first person here for
Are you
these
serious?
ones. Yes.
I will
I
be
think
here all the time. Oh my
I think 'cause
God.
it's Friday night, like people want to relax. It's the
Hmm.
weekend.
Yeah, I get
Yeah.
it.
But sometimes like when something comes up, I might like have to cancel it, like the Friday
Right.
ones.
Yeah.
But yeah, you'll see in the school like if there's nothing there, like the when the next event is.
Okay. That's
Yeah.
perfect. No, that's totally fine.
Uh-huh. And after the summer, I took one to see, and that was the first person, like first quarter back in person, my second year, first quarter.
Yeah.
And then that was the quarter with Nasiri. Well, I had Nasiri two times, and then like I
Oh
failed the
no.
first midterm because like I was not used to the open note, like not no open note exam. It was closed note,
Oh
and so I
yeah.
did like below average for the first midterm. Like I did not
Oh
expect
my
that.
God. I've heard she's really or something happened. I know I don't think she's teaching anymore, but I've heard
Yeah.
from different students they're like, don't take her if you don't have
Uh,
to.
yeah. I heard that she said like her goal is to like destroy pre-med dreams, like pre-health people's dreams.
Oh
I
no.
know.
Well,
It's
your dreams
crazy.
were destroyed.
Yeah, I know. And then after I finished OChem, during winter break, I got an email from AETC like asking me to tutor for them.
Huh.
Uh, and I was like in Lake Tahoe that time at like an Airbnb with my friends, and I was like asking them should I like take the job or not, and then because I wasn't sure, and they were like just try it out. If I don't like it, I can just quit.
Yeah.
And then when I tried it out, I sucked at it like so much. Like I had to like look at my notes all the time, ask other tutors for help. I was so bad at it at the beginning.
Look at you now. Oh my gosh.
I know, because over time, like you just see the material over and over and over again, and
Yeah.
then like, yeah, that was like 2022, like winter 2022, January 2022. So like it's been 3 years since I
Wow.
tutoring 2022, 23, 24. Yeah, 3 years.
Holy moly. That's
Like it's,
awesome. That is so cool.
and then a year in, like March 2023, like a little bit over a year, I I, I started to get like a lot of requests on private tutoring, like at the ATC, and
Yeah.
then that's what like made me like start like the private tutoring
Oh,
thing.
I see. Okay. Yeah, I bet. I mean, you're really good at teaching. I'm sure you had problems in the beginning, but
Yes.
you explain it really well.
Yes, like the prep hours at ATC, like I had to overuse the prep hour. Like I prepared like way more than I was paid for
Oh,
to
really?
before my shifts. Right? Because
Aw.
like I was like nervous to go. Like I did not look forward for the shifts at all. Because like I did not know. But then over time it like went down and down and down. You 1 hour, like what 3 hours to 2 hours to 1 hour, and then eventually
Yeah.
like I just came in without preparing at all, and I still get paid for the prep hours. Like you can submit the prep hours online,
Oh
but
my
then
gosh.
eventually I didn't have to use it, but I still got the
Wow.
yeah.
That's awesome.
Uh-huh.
That's really cool. I didn't know that.
Uh-huh.
I mean, you just, yeah, I'm sure, and also like talking people through it all the time kind of helped your understanding.
Yes, and also
Well,
like I gain new perspectives like from how different people see things. So like when the students struggle with things and they tell me like how they see it, like I use like that to tutor like future students too, like to
oh,
see like if it helps
really?
them. Yeah.
Yeah, that's smart.
Yeah.
Well,
Mhm.
thank you. I mean, I know we have a
Yeah.
meeting tomorrow as well. Um,
Uh-huh.
unless you want to go over stuff, uh,
Yeah. I prepared like
up tonight.
these or notes for you for lectures 1 to 5, the ones that
Oh,
you
wow.
sent me before today. Um, so you could look through these, and these are the new ones that you just sent me, 6 and 7, right here,
Yes.
right? Tomorrow, my plan is to go over 6 and 7 for sure because that's the
Yes.
new ones. The like post quiz, right? Post quiz,
Yes.
material, especially the aromatic rings, the practice quiz, and send me your graded quiz on your Google Drive. And then
Okay.
when I have time to, I'll make a video for you and post it on your drive to like go
Okay.
over all of it. Actually, like go all of your mistakes, what you went wrong, and then how to avoid them in the future, and then like
Okay.
go through the key for you to watch.
Okay. Yeah, that's no problem at all. I
Yeah.
can totally do that.
Uh-huh. I see. It's good. So we'll call it here and then
Yeah.
we'll meet again tomorrow, 11:30 a.m. to 12:30 p.m.
Yes.
Uh-huh.
Yes,
Sounds
that
good.
still works for you.
Yeah, that still works for me.
Okay.
Uh-huh.
I'm really flexible too, so if you have any like anything that's going on, just
Uh-huh.
let me know.
Yeah, uh-huh. Sounds good, Madison.
Okay. Well, thank you so much. I'll keep an eye out and then I will upload that stuff right now.
Mm-hmm. Okay, yes.
Awesome.
Sounds
Thank
good.
you. I hope
Mhm.
you have a good night.
Yeah, you too, Madison.
Tomorrow.
Yeah, see you tomorrow.
Okay, bye.
Bye. Good night.